Tonight, we are going to answer a question that almost nobody can fully answer. And here is what makes that strange. The answer affects every single hour of your day. It has affected every hour of every day of your entire life. It is happening right now, at this exact moment, while you are lying in the dark listening to these words. But if someone stopped you on the street tomorrow and asked you to explain it, really explain it, from the beginning, all the way through, most people cannot. Most engineers cannot. Even most physicists, if you ask them to explain the full chain from start to finish, would have to stop and think. The question is this: you flip a switch, a light comes on. What actually happened? Not in your house, not in the wire behind your wall. Before that, long before that, in a building you have probably never seen, surrounded by walls of reinforced concrete, several feet thick, somewhere between 50 and 300 miles from where you are lying right now. What happened in there? Tonight, we are going to find out slowly, from the very beginning, and by the time we are done, by the time the last fact has settled and the last image has formed in your mind, you will never flip a light switch again without knowing, somewhere in the back of your mind, exactly what you just did. If these quiet journeys through the history of science and engineering help you rest tonight, consider leaving a like or subscribing. But for now, let the screen go dark, let your breathing slow, and let us begin somewhere in the world right now. Not metaphorically, not approximately, but literally, at this exact moment as you listen. There is a room. The room is underground, or at least partially underground, surrounded by walls of concrete and steel, so thick that a car driving into them at full speed would not penetrate them. The air inside is cool and controlled, the temperature maintained within narrow tolerances by systems that run continuously, day and night, without pause. The room smells faintly of something metallic, something clean and industrial, the kind of smell that belongs to places where serious work is done by serious machines, and where human beings are present only to watch and to manage and to make certain that everything continues exactly as it should. Inside this room, something extraordinary is happening. Something that physicists spent 40 years trying to understand. Something that governments spent billions of dollars trying to control. Something that engineers spent decades trying to make safe and reliable and quiet enough that the people who benefit from it, which is nearly everyone alive in the developed world, would never have to think about it at all. Atoms are splitting right now, continuously, in a controlled, deliberate, precisely managed chain reaction that has been running for months or years, generating heat at a rate so steady and so reliable that the engineers monitoring it from their control room upstairs can predict its output hours in advance to within a fraction of a percent. That heat is boiling water. The water is becoming steam. The steam is spinning a turbine at exactly 1,500 rotations per minute, or 1,800, depending on where in the world this particular plant is located. The turbine is turning a generator. The generator is producing electricity, and that electricity is traveling right now at very nearly the speed of light through transformers and transmission lines and substations and the distribution network that runs beneath your street to the switch on your wall. You flipped it, the light came on, and the chain that connected your finger to those splitting atoms, a chain that stretches back not just across the miles between your home and that concrete building, but across decades of physics and engineering and human courage and human error. That chain has been running since before you woke up this morning and will still be running after you fall asleep tonight. Here is the thing that most people do not know about nuclear power, and this is the detail that changes everything once you understand it. A nuclear power plant is not primarily a nuclear facility. It is a steam engine. That is it. At its heart, beneath all the concrete and the safety systems and the instruments and the specially trained operators and the regulations and the international inspection regimes, beneath all of that, a nuclear power plant is a machine for boiling water. The reactor produces heat. The heat boils water. The water becomes steam. The steam spins a turbine. The turbine drives a generator. This is the same sequence of events that happens in a coal power plant. The same sequence that happens in a natural gas plant. The same sequence that happens in a plant that burns wood or oil or municipal waste. The only difference, the single, essential, revolutionary difference, is the source of the heat. In a coal plant, the heat comes from burning coal. In a nuclear plant, the heat comes from splitting atoms. And the reason splitting atoms produces so much more heat than burning coal, so much more heat that a single nuclear fuel pellet the size of your fingertip contains as much energy as 149 gallons of oil or 157 gallons of regular gasoline or 17 fils cubic feet of natural gas. The reason for that extraordinary difference is a story that begins not in an engineering laboratory, but in a patent office in Switzerland in 1905 with a 26-year-old man who was thinking about light. But we will get to Einstein in the next chapter. For now, there is something else worth understanding. Something that sets the scene for everything that follows. Because before there were nuclear power plants, before there were nuclear reactors of any kind, before anyone had demonstrated that the energy inside an atom could be released in a controlled and sustained way, the idea of nuclear power was not an engineering problem. It was not even a physics problem. It was a philosophical question. Is there energy inside the atom? And if there is, can it be released? And if it can be released, can it be controlled? For most of the early 20th century, even the physicists who understood atomic structure best were deeply uncertain about the answers to all three of those questions. So, Ernest Rutherford, the New Zealand-born physicist who discovered the nucleus of the atom in 1911, who first understood that almost all of an atom's mass is concentrated in a tiny central point. Ernest Rutherford said publicly in 1933 that anyone who thought practical energy could be extracted from atomic nuclei was talking moonshine. Moonshine. His word. He was wrong. But he was not being foolish. He was being careful. The way scientists are careful when they have spent decades learning how treacherous overconfidence can be. The world that would prove him wrong was already being built. In laboratories across Europe and America, by people who were asking the questions he had decided to set aside. And the answer, when it came fast. Let me tell you something about the world in the early decades of the 20th century that is easy to forget when we look back at it now. The people living in it did not know what was coming. They did not know about nuclear power or nuclear weapons or the Cold War or any of the things that the word nuclear would come to mean. In the second half of the century, they lived in a world lit by electricity generated from coal and oil, cooled in summer by ice cut from frozen ponds in winter, connected by telegraph wires and early radio transmissions and railways and ships that crossed the ocean in days rather than hours. It was a world that was changing fast, faster than any previous generation had experienced. But the changes were visible, physical, comprehensible. A new building going up, a new machine on the factory floor, a new aircraft crossing the sky. What was happening in the physics laboratories was invisible. The physicists working on atomic structure in the 1920s and 1930s were working on problems so abstract, so remote from anything that could be touched or seen or bought or sold, that most educated people, let alone ordinary people, had no idea what they were doing or why it might matter. They were asking questions about things so small that no instrument of the era could directly observe them. They were developing mathematical frameworks to describe behaviors so counterintuitive that even the physicists themselves argued bitterly about what the mathematics was actually saying. And they were, without knowing it, assembling the pieces of something that would reshape the world, one piece at a time. In laboratories that smelled of chemicals and machine oil, on chalkboards covered in equations that most people could not read, in papers published in journals that most people had never heard of. The piece that made everything else possible was an equation. 4 characters. E equals mc squared. Here is what that equation actually means. Not the mathematics, the meaning. Imagine you are holding a small stone, an ordinary stone, the kind you might pick up on a beach. It weighs perhaps 50 grams. Half a chocolate bar. Inside that stone, at a scale far too small to see, are atoms. Billions upon billions of atoms, each one a nucleus surrounded by electrons. Each nucleus held together by forces so strong that the word strong does not really do them justice. Einstein's equation says that the mass of that stone The actual physical mass of it, expressed in kilograms, is equivalent to an amount of energy. The conversion factor between mass and energy is the speed of light squared. The speed of light is approximately 300 million meters per second. Squared, that number is approximately 90 quadrillion. What this means in practice is that the energy equivalent of that 50-gram stone, if it could be completely converted to energy, would be approximately 4.5 petajoules, enough to power a large city for several days, from a stone you picked up on a beach. This is not a metaphor. This is not an approximation. This is what the equation says, and the equation is correct, and the energy is real. The question that consumed physics for 40 years after Einstein published his equation was simply this: can any of it actually be released? The answer came on a December afternoon in 1938 in a laboratory in Berlin. Two chemists, Otto Hahn and Fritz Strassmann, were bombarding uranium atoms with neutrons. This was a common experimental technique of the era. You fire neutrons at atoms and observe what happens. Usually what happens is predictable, manageable, consistent with what theory would expect. What happened in Berlin on that December afternoon was none of those things. The experiment was producing barium. Barium is not a heavy element. Uranium is. If you bombard a uranium atom with a neutron, you might expect to get a slightly heavier or slightly different uranium atom. You might expect various byproducts of nuclear reactions that physicists had cataloged over years of experimentation. You would not expect barium. Barium is approximately half the atomic weight of uranium. Getting barium from uranium means that something fundamental had happened to the uranium nucleus, something that had not been observed before, something that Hahn and Strassmann could not fully explain. They wrote a letter. They wrote it to Lise Meitner, their colleague, a Jewish physicist, a Jewishist who had been working with them in Berlin, until the political situation in Germany had made her position impossible, and who had recently fled to Sweden, where she was living in temporary accommodation in a small coastal town called Kungälv. Meitner read the letter. She was spending Christmas with family. Her nephew, Otto Frisch, was visiting. On the morning after she received the letter, the two of them went for a walk in the snow outside the town. Meitner was 60 years old. Frisch was 34. They walked through the winter landscape, bare trees, pale sky, the particular silence that snow creates, and they worked out what Hahn and Strassmann had observed. The uranium nucleus had split, not chipped, not shed a particle or two. Split, divided into two roughly equal pieces, like a drop of liquid dividing into two smaller drops. And when Meitner calculated the energy that would be released by that splitting, when she applied Einstein's equation to the mass difference between the original uranium nucleus and the two fragments it had become, the number that came out was real and large and matched the equation exactly. The marble in the stadium had cracked open. And what was inside was not nothing. Meitner and Frisch wrote up their findings quickly. The paper was published in January 1939 in the British journal Nature. It was read within weeks by physicists on several continents, and almost everyone who read it understood immediately what it implied. Not just that energy could be released from the uranium nucleus, but that if the splitting of one nucleus released neutrons, and it did, and if those neutrons could strike other uranium nuclei and cause them to split, and they could, then you had the possibility of a chain reaction, each split causing more splits, each neutron producing more neutrons. The reaction sustaining and amplifying itself, releasing more energy with each generation, potentially continuing indefinitely, as long as there was uranium fuel to sustain it. Uncontrolled, this was a bomb controlled, slowed, managed, kept at a steady rate. This was an energy source. The question was whether the controlled version was actually possible. Whether human beings could take a chain reaction, a process that in an uncontrolled state releases its energy in a fraction of a second, and make it run slowly, steadily, for months. The person who answered that question was a 41-year-old Italian physicist standing in a squash court under a football stadium in Chicago on the afternoon of December 2nd, 1942. But that is the story of the next chapter. For now, the question has been asked. The marble has cracked open. The energy is real. And somewhere in a patent office in Bern, Switzerland, nearly 40 years earlier, a 26-year-old man who spent his days examining other people's inventions and his evenings thinking about light had written 4 characters that turned out to contain everything. E equals mc squared. The switch had been found. It just needed someone to flip it. Imagine you are standing in the middle of a football stadium, not sitting in the stands, standing on the field itself, the playing surface, the 50-yard line, the center of everything. You can see the seats rising around you in every direction, tier after tier, all the way up to the highest rows near the roof, the scoreboard at one end, the goalposts at both ends, the entire enclosed space of the stadium surrounding you. Now imagine that this stadium, every cubic meter of it, from the field beneath your feet to the roof above your head, represents a single atom, the whole thing. One atom. And now imagine a marble, a single glass marble, the kind children play with, sitting on the field at the 50-yard line. That marble is the nucleus of the atom. Everything else, every seat, every aisle, every cubic meter of air between the field and the roof is either empty space or occupied by electrons so small and moving so fast that they are less like objects and more like a blur, a probability, a tendency to be somewhere rather than a thing that is somewhere. The atom is almost entirely nothing, almost entirely empty, the marble and the stadium. And here is the fact that changes everything else in tonight's story. The fact that makes nuclear power not just possible, but inevitable. Once you understand it, almost all of the atom's mass is in the marble, not some of it, not most of it, almost all of it. More than 99.9% of the total mass of the atom is concentrated in that tiny central nucleus, in that marble on the 50-yard line. And inside that marble is stored an amount of energy so vast that the physicists who first calculated it did not believe the number. They checked it again. The number was the same. They checked it a third time, using different methods, different assumptions, different mathematics. Still the same. The marble contained more energy than anyone had imagined any physical object could contain. The question was how to open it. Let us stay inside the marble for a moment, because what happens in there is the entire story. The nucleus of an atom, our marble, is made of two types of particles, protons and neutrons. Protons carry a positive electrical charge. Neutrons carry no charge at all. They are electrically neutral, which is where their name comes from. Both types of particles are packed together inside the nucleus in extremely close proximity, and this immediately raises a question that you might already be formulating. Positive charges repel each other. Whereas this is a fundamental property of electricity. Like charges push apart, opposite charges attract. If you have tried to push two magnets together with the same pole facing each other, you have felt a version of this force. The repulsion is real and it is strong. So, why do the protons inside the nucleus not fly apart? There are multiple protons in every nucleus except hydrogen. They are packed together in an extremely small space. The electromagnetic repulsion between them should be, by any ordinary calculation, more than enough to blow the nucleus apart. And yet, nuclei exist. They are stable. They hold together. The answer is something that does not have a good everyday analogy, because nothing in everyday experience behaves the way it does. Physicists call it the strong nuclear force. The strong nuclear force is the strongest force in nature, not slightly stronger than the electromagnetic force that is trying to blow the nucleus apart, not twice as strong or 10 times as strong, approximately 100 times as strong. At the distances inside the nucleus, the strong nuclear force overwhelms the electromagnetic repulsion completely. It binds the protons and neutrons together with a grip so powerful that, under normal circumstances, nothing can break it. Under normal circumstances. Here is the critical detail, the one that makes everything else possible. The strong nuclear force only operates across extremely short distances. Distances smaller than the nucleus itself. Step outside that range. Move even slightly further away than the diameter of a proton, and the strong force drops to essentially zero. It simply stops working. This is the combination that makes nuclear energy real. Enormous binding energy at short range, zero influence at any longer range. What it means in practice is this: if you could somehow get a neutron, not a proton, a neutron, with no electrical charge, and therefore no electromagnetic repulsion to overcome. If you could get a neutron close enough to a nucleus, close enough for the strong force to grab it, the nucleus would absorb it. And in certain atoms, heavy atoms, atoms with large nuclei, where the protons are already pushing against the limits of what the strong force can hold together, absorbing an extra neutron is enough to push the nucleus past its breaking point. The nucleus becomes unstable, it wobbles, and then it does something that Otto Hahn and Fritz Strassmann observed in Berlin in December of 1938 and could not initially explain. It splits. The element that splits most usefully, most reliably, most controllably, most productively is uranium. Specifically, a particular form of uranium called uranium-235. Uranium is the heaviest, naturally occurring element on Earth. Its nucleus contains 92 protons. More protons than any other element that occurs naturally, which makes it inherently unstable in ways that lighter elements are not. It was discovered in 1789 by a German chemist named Martin Heinrich Klaproth, who named it after the planet Uranus, which had been discovered 8 years earlier. For most of the century after its discovery, uranium was used as a yellow pigment in ceramic glazes. Uranium glass, glass with small amounts of uranium mixed into it, produces a distinctive green glow under ultraviolet light, and it was fashionable in the 19th century for decorative objects. Wine glasses, vases, small ornamental bowls. People drank from uranium glass without any particular concern because in the 19th century, no one fully understood what radioactivity was, or that uranium was radioactive, or what radioactivity did to living tissue. The radioactivity of uranium was discovered in 1896 by a French physicist named Henri Becquerel, in circumstances so accidental that they deserve a moment of description. Becquerel was studying fluorescence, the property that certain materials have of absorbing light and then re-emitting it. He had been using uranium salts in his experiments and had developed a method of exposing photographic plates by leaving uranium-coated materials in sunlight. In February of 1896, Paris had several overcast days in a row. No sunlight. Becquerel set aside his experiment and put the photographic plates, still wrapped in their black paper, with uranium salts resting on top of the paper, in a drawer. Several days later, he developed the plates anyway, expecting nothing. The plates were strongly exposed. The uranium had affected the photographic plates through the black paper wrapping, through several days of storage in a dark drawer, without any sunlight involved at all. Becquerel had discovered radioactivity, the property of certain elements to spontaneously emit radiation by accident, because it rained in Paris for a week. Marie Curie took Becquerel's accidental discovery and made it into a science. She was 28 years old when she began her systematic investigation of radioactivity in 1897. A Polish-born physicist working in Paris, one of the very few women in European science at the time, working in conditions that her male colleagues would not have tolerated for a week. Her laboratory was a converted shed, leaky roof, earthen floor, no proper ventilation. She worked in it for years, processing enormous quantities of radioactive material by hand, stirring boiling cauldrons of pitchblende, a uranium-containing ore, with an iron rod almost as large as herself, breathing the fumes, handling the material directly. She discovered two new elements: polonium, which she named after her homeland of Poland, and radium, whose radioactivity was almost 2 million times more intense than uranium's. She won 2 Nobel Prizes, one in physics in 1903, shared with her husband Pierre and with Becquerel, one in chemistry in 1911, awarded solely to her, the first person in history to win Nobel Prizes in 2 different scientific disciplines. She died in 1934 of aplastic anemia, a disease of the blood-forming cells, almost certainly caused by decades of radiation exposure. From handling radioactive materials without protection at a time when no one fully understood what radiation did to the human body over long periods. Her notebooks are still radioactive. They are kept in lead-lined boxes in the Bibliothèque Nationale de France. Researchers who wish to examine them must sign a waiver acknowledging the radiation risk. The notebooks are over 100 years old. They are still dangerous. By the time Hahn and Strassmann were working in Berlin, in 1938, the physics of the atom was well understood in outline, if not in every detail. Physicists knew about protons and neutrons. They knew about the strong nuclear force, though they did not fully understand it. They knew that uranium was radioactive, that it spontaneously emitted particles and energy as its nucleus slowly rearranged itself toward a more stable configuration. What they did not know, what nobody knew until that December afternoon in Berlin, was that a uranium nucleus could be induced to split completely into 2 roughly equal pieces, not shed a particle, not rearrange itself slightly. Split. The word that Lisa Meitner and Otto Frisch chose for this process in their paper published in January 1939 was borrowed from biology: fission, the division of a cell into 2 daughter cells. The same word applied to the division of a nucleus into 2 daughter nuclei. And when Meitner sat down with the mathematics, when she calculated what happened to the mass during fission, when she accounted for the mass of the original uranium nucleus and compared it to the combined mass of the 2 fragment nuclei, and the neutrons released, she found something that Einstein's equation had predicted, but that nobody had yet observed directly. The fragments weighed less than the original nucleus, not much less, a tiny fraction less, approximately 1/5 of 1% less. But even a tiny fraction of mass, multiplied by the speed of light squared, is an enormous amount of energy. The missing mass had become energy. Exactly. Einstein had said it would in a patent office in Bern 33 years earlier. Here is what fission actually looks like at the level of the nucleus. A neutron, traveling at speeds that vary depending on the reactor design, but, let us say, at a relatively slow speed, slow enough that the uranium nucleus has time to absorb it rather than deflect it. A neutron strikes a uranium-235 nucleus. The nucleus absorbs the neutron for a fraction of a second, an almost incomprehensibly brief interval. The nucleus holds the extra neutron, but uranium-235 was already on the edge of stability. The extra neutron is too much. The strong force, which was barely managing to hold 92 protons and 143 neutrons together, cannot manage 92 protons and 144 neutrons. The nucleus begins to deform, to stretch, to elongate, from a sphere into something more like a dumbbell. As it elongates, the distance between the two ends increases, and as that distance increases, the strong force, which drops to zero at distances greater than the diameter of a proton, begins to lose its grip on the two ends. But the electromagnetic repulsion between the protons does not drop off. The protons at the two ends are still pushing against each other. The strong force lets go. The electromagnetic repulsion takes over. The nucleus snaps apart into two fragments, typically barium and krypton or similar combinations, traveling away from each other at approximately 3% of the speed of light. And in the instant of that snapping apart, 2 or 3 neutrons are released as well, free neutrons, moving outward from the fission event, available to strike other uranium-235 nuclei, which will absorb them, which will split, which will release more neutrons. This is the chain reaction, each split making the next split possible. Each generation of neutrons enabling the next generation of fissions. The reaction sustaining itself, amplifying itself, continuing as long as there is uranium fuel and as long as enough of the released neutrons are striking other uranium nuclei, rather than escaping the fuel or being absorbed by other materials. Uncontrolled, all the energy released in a fraction of a second. This is what destroyed Hiroshima on August 6, 1945. Controlled, the reaction rate carefully managed, the energy released slowly and steadily over months. This is what is happening right now inside those thick concrete walls, producing the electricity that powers the light in your ceiling. The difference between a bomb and a power plant is not the physics. The physics is identical. The difference is control, and the man who first demonstrated that control was possible, who first showed that a chain reaction could be started, and, crucially, stopped, was standing in a squash court under a football stadium in Chicago on the afternoon of December 2nd, 1942, holding a slide rule and waiting for lunchtime to end. His name was Enrico Fermi, and what he was about to do would change the world so completely that the world he left behind him, the world of coal and oil and the slow, expensive, dirty burning of ancient carbon would never fully come back. The next chapter begins at 9:45 in the morning. It ends 28 minutes later with paper cups of Italian wine and with the quiet, certain knowledge that the marble in the stadium had finally been opened. Imagine you are Enrico Fermi. It is the morning of December 2nd, 1942. You are standing in a converted squash court beneath the west stands of Stagg Field, the football stadium of the University of Chicago. And in front of you is something that has never existed before in the history of the world. A pile of graphite and uranium blocks stacked in 57 layers, 20 feet high, shaped roughly like a flattened sphere. It took 49 days to build. Hundreds of graphite blocks, each one carefully machined to precise dimensions, each one positioned by hand. Thousands of uranium slugs embedded within them at calculated intervals. The whole structure sitting on a wooden frame, surrounded by a balloon cloth, inflated to control humidity in a room with a ceiling low enough that the upper layers of the pile are within arm's reach of the ceiling above. The room smells of graphite dust. Graphite dust is fine and black, and it settles on every surface, every piece of clothing, every exposed patch of skin. The men who built this structure over the past 7 weeks have been breathing it, wearing it, carrying it home in the evenings in the fabric of their coats. You have been breathing it too. You do not particularly care, because in a few hours, if the mathematics you have been checking and rechecking for months is correct, this pile of graphite and uranium is going to do something that no structure on Earth has ever done. It is going to sustain a nuclear chain reaction, and you are going to control it. Enrico Fermi was 41 years old on the morning of December 2nd, 1942. He had been born in Rome in 1901, the youngest of 3 children of a railway official. He had taught himself physics as a teenager from textbooks borrowed from a market stall near his home, reading them so completely and so deeply that by the time he arrived at university, he knew more than some of his professors. He was the kind of physicist who existed perhaps once in a generation, a man equally comfortable with theoretical abstraction and experimental craft, capable of deriving the equations and then walking into a laboratory and building the apparatus to test them. He won the Nobel Prize in Physics in 1938 at the age of 37 for his work on neutron bombardment of atomic nuclei. He traveled to Stockholm in December of that year to receive it. He did not go home afterward. His wife, Laura, was Jewish. The racial laws that Mussolini's government had enacted in Italy that year made their position increasingly dangerous. The Nobel Prize ceremony gave them a reason to leave Italy with their children without attracting undue attention. They sailed from Southampton to New York in January 1939. Fermi joined the faculty of Columbia University. Then, as the project that would eventually become the Manhattan Project began to take shape, he moved to the University of Chicago, where a team had been assembled to achieve something that had never been achieved: a sustained, controlled nuclear chain reaction. The theoretical possibility of a chain reaction had been understood since Lise Meitner's paper in January 1939. If a uranium-235 nucleus absorbs a neutron and splits, it releases 2 or 3 more neutrons. Those neutrons can strike other uranium-235 nuclei, causing them to split, releasing more neutrons still. The chain sustains itself. In principle. In practice, there were problems. The first was that natural uranium is mostly uranium-238, not uranium-235. Uranium-235, the form that fissions readily, makes up only 0.7% of natural uranium. Uranium-238 does not fission easily. Worse, it tends to absorb the neutrons that would otherwise keep the chain reaction going. In a mass of natural uranium, most of the neutrons released by fission events are absorbed by uranium-238 before they can reach another uranium-235 nucleus. The chain dies before it can sustain itself. Fermi's solution to this problem was elegant in its simplicity. Slow the neutrons down. Fast neutrons, the neutrons released immediately after a fission event, are more likely to be absorbed by uranium-238. Slow neutrons, neutrons that have been slowed to speeds more compatible with the thermal energy of their surroundings, are much more likely to be absorbed by uranium-235 and cause fission. The way to slow a neutron is to surround it with a material whose nuclei are similar in mass to the neutron. When a moving particle strikes another particle of similar mass, it transfers most of its energy in the collision, the way a billiard ball striking another billiard ball transfers most of its momentum. The best practical materials for this purpose are water and graphite. Fermi chose graphite. And so the structure being built under Stagg Field was not just a pile of uranium. It was a pile of uranium embedded in graphite. The graphite serving as a moderator, slowing the neutrons released by fission down to speeds where they were far more likely to cause another fission than to be absorbed uselessly by uranium-238. The second problem was control. A chain reaction, by its nature, tends to amplify itself. Each generation of neutrons is larger than the previous one. If nothing intervenes, the reaction accelerates. The energy release increases. The temperature rises. In an uncontrolled system, this process continues until something stops it. Either the fuel is exhausted or the heat becomes so extreme that the fuel vaporizes and disperses, ending the reaction. Neither of these outcomes is useful for a power source. What was needed was a way to regulate the neutron population, to absorb some of the excess neutrons, the ones beyond what was needed to sustain the reaction at a steady rate, so that the chain reaction could be held in balance. One neutron from each fission causing exactly one more fission. Not more, not fewer, Fermi's solution was cadmium. Cadmium is a metal with an extraordinary appetite for neutrons. A cadmium nucleus absorbs neutrons with an efficiency that makes it, for this purpose, almost perfect. Long rods of cadmium inserted into the pile would absorb neutrons and slow or stop the reaction. Withdraw the rods, and the neutron population would rise. Insert them, and it would fall. The control rods were the throttle of the reactor, and the safety system, the last line of defense if anything went wrong, was a team of men standing on a balcony above the pile, holding buckets of cadmium solution. 3 men, 3 buckets. If the control rods failed, if the reaction began to run away, the men on the balcony would pour their cadmium solution over the pile. This was the safety system for the world's first nuclear reactor. 3 men and 3 buckets. The team that built Chicago Pile 1. The official designation for the structure under Stagg Field was approximately 49 people. Physicists, engineers, graduate students. Some of them fully understood what they were building and what it was for. Others understood pieces of it. All of them had signed secrecy agreements so strict that they could not tell their families what they were working on, or even where they worked. Laura Fermi, at home with their children, knew that her husband was doing war research of some kind. She did not know what kind. The construction began on November 16, 1942. The work proceeded layer by layer. Each layer of the pile was carefully planned. The precise arrangement of solid graphite blocks and uranium-containing blocks, calculated to produce the correct geometry for the chain reaction. The uranium came in 2 forms: uranium oxide powder, packed into pseudospheres, and solid uranium metal, machined into cylindrical slugs. The workers who machined the graphite blocks and handled the uranium did so in conditions that would horrify a modern safety inspector. No respirators for the graphite dust. Minimal protective equipment for the uranium. They went home in the evenings smelling of graphite. Their skin was gray with it. Their clothes were gray with it. They came back the next morning and kept building. By December 1st, 57 layers had been completed. Fermi's calculations told him that the pile was ready, that the geometry and the materials were correct, that the chain reaction could be achieved. On the morning of December 2nd, the team assembled. Fermi arrived early. He was wearing his usual working clothes: dark trousers, a shirt, a jacket. He carried his slide rule, a physical calculating device consisting of logarithmic scales on a wooden base, accurate to 3 significant figures. There were no electronic computers in 1942, at least none that could do what Fermi needed, and the slide rule was his primary calculation tool. He set up his instruments. He reviewed the readings from the neutron counters surrounding the pile. He satisfied himself that everything was in the correct state. Then he explained what was going to happen to the assembled team. The control rods would be withdrawn in carefully measured increments. At each step, the neutron count would be measured and compared to Fermi's predictions. The process would be slow, methodical. There would be no hurry. If at any point the readings diverged from the predictions in an unexpected way, the control rods would be reinserted, and the experiment would stop until the discrepancy was understood. He was calm as he explained this, precise in his language. The people who were there later described his manner as professorial, the manner of someone explaining a problem that has been thoroughly analyzed and whose solution, while not yet demonstrated, is not seriously in doubt. At 9:45 in the morning, the experiment began. The process of withdrawing the control rods was not dramatic. It was, if anything, the opposite of dramatic. It was methodical, careful, incremental. Fermi would call out an instruction: withdraw the rod by a specified amount. A physicist named George Weil was responsible for the rod that would be withdrawn last. He would make the adjustment. The neutron counters would register the change. Fermi would check the readings against his predictions. He would make a note. He would call out the next instruction, step by step. The neutron count rising with each step, then stabilizing as the neutron population found its new equilibrium. The Geiger counters produced a clicking sound, a rapid, irregular ticking that became faster as the neutron count rose and slower as it stabilized. At approximately 11:30 in the morning, the experiment reached a critical point. The clicking rate was higher than it had been at any previous step. The neutron population was approaching the level at which the chain reaction would become self-sustaining. Fermi checked his instruments. He checked his slide rule. He looked at the readings for a moment in silence. Then he said, "Let us go to lunch." Not because anything was wrong, because it was lunchtime. This detail, the lunch break, is one of the things that makes Fermi's conduct on December 2nd extraordinary in retrospect. The world's first nuclear chain reaction was 45 minutes away. The neutron count was within. There is a question that almost nobody asks. Not because it is an unimportant question, because the answer has always been available. In textbooks, in documentaries, in the explanations that physicists and engineers have been giving to journalists and politicians and curious members of the public for 70 years. The question is this: inside a nuclear power plant, what is actually happening? Not in general terms. Not. Fission produces heat which makes electricity. That summary you have probably heard before, and that contains everything and explains nothing, but actually happening, step by step. From the uranium pellet in the fuel rod to the current in the wire behind your wall. Most people, if they are honest, cannot answer this question. Most people have a vague impression of something dangerous and complicated happening inside thick concrete walls, producing electricity by some process that feels more like magic than engineering, supervised by people in white coats who understand things that ordinary people are not equipped to understand. Tonight, we are going to dissolve that impression completely. Because the truth is not magic. It is not beyond ordinary understanding. It is, at its core, a story about boiling water, the oldest and most fundamental engineering process in human history, applied to the most concentrated energy source the planet contains. Let us go inside the fuel, where everything begins, the story of how a nuclear power plant produces electricity begins not in the reactor, not in the control room, not in the vast concrete dome that houses the whole operation. It begins in a mine. Uranium ore is extracted from the ground in several countries: Kazakhstan, Canada, Australia, Namibia, and others. The ore itself is unremarkable in appearance. It looks like rock because it is rock, a dark, dense mineral called pitchblende, or a yellowish ore called carnotite, or any number of other uranium-bearing formations that occur naturally in certain geological environments. The uranium content of the ore is typically small, a few tenths of a percent by weight, sometimes less. To get useful quantities of uranium out of the ore requires a process called milling, in which the ore is crushed and treated with chemicals that dissolve the uranium and allow it to be separated from the surrounding rock. The product of this process is a powder, bright yellow, the consistency of fine sand. It is called yellow cake. Yellow cake is uranium oxide, a chemical compound of uranium and oxygen. It is mildly radioactive. It is not weapons grade. It is not reactor fuel. It is the beginning of a long processing chain that will eventually transform it into something that can sustain a chain reaction. That processing chain begins with conversion. The yellow cake is converted to uranium hexafluoride, a compound that can be processed as a gas. Then comes enrichment. Natural uranium, as it comes out of the ground, is a mixture of two forms, two isotopes of the same element. Uranium-238 makes up approximately 99.3% of natural uranium. Its nucleus contains 92 protons and 146 neutrons. It is radioactive, but it does not fission readily when struck by slow neutrons. It is, from the perspective of a nuclear reactor, largely inert. Uranium-235 makes up approximately 0.7% of natural uranium. Its nucleus contains 92 protons and 143 neutrons. It fissions readily and reliably when struck by slow neutrons, releasing energy and more neutrons in the process, 0.7%, 7 atoms out of every 1,000. This is too low a concentration to sustain a chain reaction in most reactor designs. The neutrons released by fission of uranium-235 atoms are too likely to be absorbed by the surrounding uranium-238 before they can reach another uranium-235 nucleus. Enrichment is the process of increasing the proportion of uranium-235. The most common method is gas centrifuge enrichment. The uranium hexafluoride gas is fed into cascades of centrifuges, machines that spin at extremely high speeds, tens of thousands of rotations per minute. creating centrifugal forces so powerful that the slightly heavier uranium-238 hexafluoride molecules are pushed to the outside of the spinning gas, while the slightly lighter uranium-235 hexafluoride molecules concentrate toward the center. The difference in mass between uranium-235 and uranium-238 hexafluoride molecules is tiny, about 1%. A single centrifuge stage produces only a small increase in uranium-235 concentration. But cascade hundreds of stages together, feed the output of each stage into the next, and the concentration builds. For commercial reactor fuel, the target is between 3 and 5% uranium-235. This is an important number. Weapons-grade uranium is enriched to above 90% uranium-235. The physics of what happens to uranium at 3 to 5% concentration and what happens at 90% are fundamentally different. Commercial reactor fuel cannot produce a nuclear explosion. The uranium-235 concentration is simply too low to sustain the kind of fast, uncontrolled chain reaction that a weapon requires. A nuclear power plant cannot blow up like a nuclear bomb. This is not a matter of safety systems or engineering choices. It is a matter of physics. The fuel will not allow it. After enrichment, the uranium hexafluoride is converted back to uranium dioxide, a ceramic material dense and hard and stable at high temperatures. The uranium dioxide is pressed into pellets, small pellets, roughly cylindrical, about the diameter of a fingertip and about as long as a fingernail. Each pellet weighs approximately 10 grams. Each pellet contains as much energy as approximately 149 gallons of oil, or 17,000 cubic feet of natural gas, or a ton of coal. 10 grams, a small cylinder of ceramic material that fits on the tip of your finger, the energy of a ton of coal. This is what makes nuclear power remarkable. Not the complexity of the reactors, not the sophistication of the engineering, the fuel itself. The extraordinary concentration of energy in a material so compact and so stable that it can be handled safely with gloved hands. The pellets are loaded into long, thin tubes, fuel rods, made of a zirconium alloy called zircaloy. Zircaloy is chosen for this purpose because it is strong. It can withstand high temperatures, and it is transparent to neutrons. It does not absorb the neutrons that need to be available to sustain the chain reaction. Each fuel rod is approximately 4 meters long and roughly 1 centimeter in diameter. It contains several hundred uranium dioxide pellets stacked end to end inside the zircaloy cladding, sealed at both ends. Hundreds of fuel rods are bundled together into fuel assemblies. A fuel assembly is a square cross-section structure, roughly 4 meters tall, with the fuel rods running vertically inside it, held in precise geometric arrangement by spacer grids. A typical reactor core contains between 150 and 250 fuel assemblies, depending on the reactor's design and power output. This is the fuel. This is where the energy comes from. 4 meters of stacked ceramic pellets in thin metal tubes, arranged in precise geometry, inside a pressure vessel, filled with the concentrated result of billions of years of geological processes and months of careful industrial preparation. The reactor core, where the chain reaction lives, the reactor core sits inside the reactor pressure vessel. The pressure vessel is a massive steel container, typically about 12 meters tall and 4 meters in diameter, with walls between 15 and 30 centimeters thick, designed to contain the reactor coolant at very high pressure and to provide the first barrier between the nuclear reaction and the outside world. Inside the pressure vessel, surrounded by coolant water, sit the fuel assemblies. Between them and around them, a second type of rod, the control rods. The control rods are made of materials with an extraordinary appetite for neutrons. Boron is the most common, a light element whose nucleus absorbs slow neutrons with remarkable efficiency. Hafnium and silver-indium-cadmium alloys are also used depending on the reactor design. The control rods can be moved vertically within the reactor core, inserted further in, or withdrawn further out by mechanisms at the top of the reactor vessel. When the control rods are fully inserted into the core, they absorb so many of the neutrons produced by the uranium fuel that the chain reaction cannot sustain itself. Every neutron produced by a fission event is captured before it can reach another uranium-235 nucleus. The reaction stops. This is the shutdown state, the default state, the state the reactor is in when it is being refueled or maintained, or when something has gone wrong and the operators need to stop everything immediately. To start the reactor, the control rods are withdrawn. Slowly, in carefully measured increments, as they withdraw, fewer neutrons are absorbed by the control rod material. More neutrons are available to strike uranium-235 nuclei. The fission rate increases. The heat generated by the chain reaction increases. The operators in the control room watch the neutron flux, the density and rate of neutron movement through the core, on their instruments, and they adjust the control rod positions to achieve and maintain the desired power level. At full power, the chain reaction is in a state called criticality, not runaway criticality, not the uncontrolled amplification of a bomb, but exactly controlled criticality, in which each fission event produces exactly enough neutron sauce to sustain exactly one more fission event. One neutron in, one fission, 2 or 3 neutrons out. Some absorbed by control rods, some absorbed by uranium-238, one remaining to cause the next fission, perfectly balanced, perfectly sustained. The reactor at full power is a system in precise dynamic equilibrium, with the operators in the control room continuously monitoring and adjusting to maintain that equilibrium. The coolant, moving the heat. The chain reaction produces heat, enormous quantities of heat, released by millions of fission events happening simultaneously every second throughout the reactor core, heating the fuel rods from the inside, conducted outward through the zircaloy cladding into the water surrounding them. That water, the reactor coolant, is the medium that carries the heat from the reactor core to the place where it can be used to generate electricity. In the most common reactor design worldwide, the pressurized water reactor, the coolant water is kept under very high pressure, approximately 155 times atmospheric pressure. At this pressure, water does not boil even at temperatures well above 300 degrees Celsius. The pressurizer, a tall, narrow vessel connected to the primary coolant loop, maintains this pressure. Electric heaters inside the pressurizer can raise the pressure if it drops. A spray system can lower it if it rises. The pressure is maintained within a narrow range, continuously, automatically, as a fundamental condition of reactor operation. The pressurized water circulates through the core, absorbing heat. It exits the reactor vessel through large pipes and travels to the steam generators. A steam generator is a large cylindrical vessel, typically about 20 meters tall, containing thousands of thin tubes through which the primary coolant flows. The primary coolant enters the steam generator hot, flows through the tubes, transfers its heat to the water on the other side of the tubes, and exits cooler. The water on the other side of the tubes, the secondary loop, is at lower pressure. When the heat from the primary loop reaches it, it boils, steam rises, and the two water systems, the primary loop that flows through the reactor and the secondary loop that flows through the turbines, never mix. They are physically separated in contact only through the thin walls of the steam generator tubes. The radioactive primary coolant stays in its sealed loop. The non-radioactive secondary steam goes to the turbines. This is an important safety feature. The steam that spins the turbines is not radioactive. The turbine halls of a pressurized water reactor are not radiation areas. Workers can enter them without radiation monitoring equipment. The turbine, converting steam to motion, the steam, leaving the steam generators, is hot, dry, and under pressure. It travels through large pipes to the turbine building, a separate structure from the reactor containment, connected to it by the steam pipes, but physically distinct, without the concrete shielding that surrounds the reactor. Inside the turbine building is the turbine. The turbine is a large machine. Its size depends on the power output of the reactor, but for a large nuclear plant, the turbine assembly might be 30 meters long and several meters in diameter. It sits on a massive steel foundation connected to the generator by a shaft running the length of both machines. The turbine works by a principle so old and so fundamental that it predates the industrial age by centuries. Steam under pressure, directed at blades, arranged around a central shaft, pushes those blades. The shaft rotates. The rotation can be used to do work. The turbines in a nuclear power plant are more sophisticated than any steam engine James Watt would have recognized. But the principle is identical. Steam pushes blades. Blades turn a shaft. The steam enters the high-pressure turbine section, expands through the first set of blades, and gives up some of its energy. It exits the high-pressure section cooler and, at lower pressure, passes through moisture separators that remove water droplets, is reheated by steam from the steam generators, and then enters the low-pressure turbine sections for a second expansion. By the time the steam exits the final turbine stage, it has given up most of its energy. It is cool and at low pressure, just above atmospheric in many designs. It enters the condenser, where cooling water flowing through tubes causes it to condense back into liquid water. That liquid water is pumped back to the steam generators to be heated and boiled again. The turbine shaft, meanwhile, is rotating at a constant speed, 1,500 rotations per minute in countries using 50 Hz electrical grids, 1,800 rotations per minute in countries using 60 Hz grids. This rotation is maintained precisely because the frequency of the electricity produced by the generator must match the frequency of the grid it feeds into. The rotating shaft is connected directly to the generator. The generator, where electricity is born, the generator is where the mechanical energy of the rotating turbine shaft becomes the electrical energy that travels through the grid to your wall. The principle was discovered by Michael Faraday in his basement laboratory at the Royal Institution in London. In 1831, Faraday was a blacksmith's son who had educated himself by reading the books he was paid to bind as an apprentice. He had no formal education in mathematics or physics. What he had was extraordinary patience, meticulous observation, and the particular intellectual courage to follow evidence wherever it led, even when it led somewhere that nobody had been before. In August and September of 1831, he demonstrated that a changing magnetic field creates an electrical current in a nearby conductor, not a static magnetic field, a changing one, a magnet moving relative to a coil of wire moving relative to a magnet. The motion is essential. The rate of change is essential. What this means for a generator is straightforward. A conductor, a coil of copper wire, rotates inside a magnetic field created by powerful electromagnets. As the coil rotates, it cuts through the magnetic field lines. The rate of change of the magnetic flux through the coil varies as the coil turns. This changing magnetic flux induces an electrical voltage in the coil. Current flows. The coil is connected to the external circuit, to the grid. The current flows out. In a large nuclear power plant, the generator might produce anywhere from 1,000 to 1,600 megawatts of electrical power. A megawatt is 1 million watts. A typical household uses approximately 1 kilowatt of power, 1,000 watts, as an average. A 1 ow megawatt nuclear plant produces enough electricity for approximately 1 million homes simultaneously, continuously, around the clock, without the variability of wind or solar, without the carbon emissions of coal or gas, without refueling for 18 months to 2 years at a stretch. From the generator to your electricity, your wall, the electricity leaving the generator is at high voltage, typically around 20 to 25,000 volts, but this is still too low for efficient long-distance transmission. Power is lost in transmission lines due to electrical resistance. The amount of power lost is proportional to the square of the current flowing through the line. So, reducing the current reduces the losses dramatically. And reducing the current while maintaining the same power means increasing the voltage. Step-up transformers at the plant. Increase the voltage to hundreds of thousands of volts, typically 230,000 to 500 volts in the United States, for transmission across the high-voltage grid. At this voltage, with correspondingly low current, the power can travel hundreds of miles with acceptably small losses. At regional substations, step-down transformers reduce the voltage for distribution. At local substations, it is reduced further. At the transformer on the pole outside your house, it is reduced to the 120 or 240 volts that your appliances use. The electricity travels from the generator to your wall in fractions of a second, faster than the speed of sound, faster than a jet aircraft close to the speed of light. And so the chain is complete. Uranium pellets, each one containing the energy of a ton of coal, sit in fuel rods in a reactor core, undergoing fission. Neutrons released by each fission event cause other uranium-235 nuclei to split. The chain reaction sustains itself, controlled by the position of the control rods, monitored continuously by the operators in the control room. The heat released by the chain reaction heats the pressurized coolant water. The hot coolant water transfers its heat to the secondary loop in the steam generators. The secondary water boils. Steam rises. The steam travels to the turbines. It pushes the turbine blades. The shaft rotates. The generator converts the rotation to electricity. The transformers step up the voltage. The grid carries the electricity across hundreds of miles. The substation steps the voltage down. The transformer on your street steps it down further. You flip the switch. The light comes on. Faraday's principle, Fermi's chain reaction, Einstein's equation, Meitner's calculation on a walk in the snow, all of it moving at the speed of light from a marble-sized ceramic pellet to the light in your ceiling. The chain from the uranium mine to your wall is long. It is complex. It involves physics that was unknown a century ago, engineering that did not exist 70 years ago, and materials that were not commercially available 50 years ago. But it is not magic. It is not beyond understanding. It is, at its heart, a very old idea applied to a very new energy source. Boil water, make steam, turn a wheel, generate electricity. The fire that boils the water is just different from any fire that came before it. It burns inside the nucleus of an atom. It burns without flame, without smoke, without the atmospheric carbon that other fires leave behind. It burns in the quiet, controlled, precisely managed heart of a reactor, surrounded by instruments and safety systems, and the careful attention of the operators who watch over it through every hour of every day. And it has been burning in reactors around the world for 70 years, quietly, continuously, in buildings you have probably never noticed, keeping the lights on. There is a moment, sometime between 3 and 4 in the morning, when a nuclear power plant becomes the quietest large building on Earth. Not silent, never silent. The machinery does not allow silence. The pumps that circulate coolant through the reactor core run continuously. The turbines spin without pause. The generators hum at their constant frequency. The ventilation systems move air through corridors and equipment rooms, and the vast spaces of the turbine hall in a steady, unceasing flow. But quiet, in the way that places become quiet when the human beings in them are fewer and more focused, and the ordinary noise of organizational life, the conversations, the meetings, the movement of people between tasks has settled into the particular stillness of the deep night. At 4 in the morning, a nuclear power plant is running at full power. It has been running at full power since the previous refueling outage ended months ago. It will continue running at full power until the next refueling outage begins. Months from now, the reactor does not slow at night because electricity demand slows at night. It does not rest on weekends. It does not observe holidays. It runs, and somewhere in the building, in a room that looks nothing like what most people imagine. When they imagine a nuclear facility, a small team of people is watching it run. Let me tell you what the control room actually looks like. Not the control rooms from films and television, the ones with red emergency lighting and banks of blinking displays and operators in white coats hovering over consoles with expressions of barely suppressed panic. The actual control room, it is a large room, often curved in its layout with a raised floor, beneath which run the cables and conduits that connect the control systems to the instruments throughout the plant. The floor is typically covered in a gray or beige industrial material, scuffed and worn in the areas where operators walk most frequently. The main panel, the C-shaped or straight-line arrangement of instruments and controls that runs along the primary working face of the room, is the visual center of everything. In older plants, this panel is a physical installation of astonishing complexity. Hundreds of individual gauges, each one monitoring a specific parameter somewhere in the plant. Hundreds of indicator lights, some green, some amber, some red, each one connected to a specific condition somewhere in the plant. Hundreds of switches, push buttons, and control handles, each one connected to a specific actuator somewhere in the plant. The combined visual effect, seen for the first time, is overwhelming. There is no obvious organizing principle visible to the uninitiated observer. The panel appears to be simply an enormous collection of things. Gauges and lights and switches and labels and numbers, arranged in a manner that seems to have accumulated over decades rather than been designed with any particular intention. This appearance is misleading. Every gauge, every light, every switch on that panel has a specific location chosen during the plant's design process. Related systems are grouped together. The most critical parameters are positioned at eye level in the most frequently occupied positions there. The arrangement has been studied and tested and refined over years of operating experience, and the operators who work in front of it every day know it the way a musician knows an instrument, not by consciously thinking about where each control is, but by having worked in front of it long enough that reaching for the right switch has become something below the level of thought. Modern plants have replaced much of the traditional analog instrumentation with digital displays. Large screens showing graphical representations of plant systems with alarm management software that prioritizes and categorizes the information demanding the operator's attention. The transition from analog to digital has made the control room visually cleaner and in many ways more manageable. But the older analog panels have something the digital systems do not. You can see everything at once. Every parameter, every system, every condition. All of it visible simultaneously to an experienced operator standing in front of the panel. Nothing hidden behind a menu. Nothing requiring a click or a navigation step to reveal. The entire state of the plant encoded in the positions of hundreds of needles and the colors of hundreds of lights, available to trained eyes in a single comprehensive glance. At 4 in the morning, an experienced operator can walk into the control room and know within 30 seconds of looking at the panel whether the plant is in a normal, expected state or whether something somewhere requires attention. There are typically 3 or 4 licensed operators on shift in the control room at any given time. The shift supervisor is the senior person in the room, the person with overall responsibility for the safe operation of the plant during their shift. They hold a senior reactor operator license, which requires years of training and experience, and passing a rigorous examination administered by the Nuclear Regulatory Authority. The reactor operator monitors the nuclear steam supply system, the reactor itself, the coolant loops, the steam generators, the pressurizer. This is the person most directly responsible for the state of the chain reaction. The turbine operator monitors the turbine generator system, the machinery that converts the steam from the reactor into electricity and feeds it to the grid. And in many plants, additional operators monitor auxiliary systems, the electrical distribution systems, the cooling water systems, the compressed air systems, the fire protection systems, the dozens of supporting systems that keep the primary process running. All of them are licensed. All of them have completed years of training, classroom instruction, simulator training, on-the-job qualification, before being permitted to operate the actual plant controls. In the United States, nuclear power plant operators are among the most extensively trained professionals in any industry. The licensing examination administered by the Nuclear Regulatory Commission has a failure rate that would not be out of place at a medical school. They work 12-hour shifts, rotating between day and night. They work in teams, the same group of people cycling through the shift rotation together. Because familiarity matters in high-stakes environments. Knowing how your colleagues think, knowing how they respond under pressure, knowing their habits and their tendencies is not a social convenience. It is a safety asset. At 4 in the morning, on a normal night, the control room is quiet. The reactor is at full power. 100% of rated thermal output, exactly where it has been for months. The coolant temperature is within its normal operating band. The steam generator, steams, are producing steam at the correct rate and pressure. The turbine is spinning at exactly 1,500 rotations per minute, or 1,800, depending on the grid. The generator is producing electricity at the rated output. Everything is normal. The reactor operator sits at the console, eyes moving periodically across the panel in the practice scan that experience develops, not staring at any one instrument, not ignoring the panel, a continuous, low-level awareness, the kind that allows a parent to hear a child stir in the next room while carrying on a conversation. The shift supervisor is at the back of the room, reviewing the shift log. The log is a continuous record of every significant event during the shift. Every parameter deviation, however minor, every test performed, every piece of equipment taken out of service for maintenance and returned to service, every notification made to the plant management or to the regulatory authority. Nothing is too small to record. This is not bureaucracy for its own sake. It is institutional memory made systematic. The log for this shift will be read by the incoming shift supervisor. At the start of the next shift, it will be reviewed by plant management. It will be available to the regulatory inspectors who visit the plant regularly and whose job is to verify that the plant is operating in accordance with its license. The paper trail of a nuclear power plant's operation is, by any standard, comprehensive. Here is what the operators are actually monitoring at 4 in the morning. The most critical parameters are the ones directly related to the nuclear chain reaction. Reactor power. The thermal power being produced by the chain reaction expressed as a percentage of the rated maximum. At full power, this reads 100%. Small fluctuations, fractions of a percent, are normal and expected, the result of minor variations in coolant temperature and density. that slightly affect the neutron behavior in the core. Coolant temperature. The temperature of the primary coolant water at the inlet and outlet of the reactor vessel. The difference between inlet and outlet temperatures is a measure of how much heat is being removed from the core. If this difference changes unexpectedly, something has changed about either the power being produced or the flow of coolant through the core. Coolant pressure, the pressure in the primary loop, maintained by the pressurizer. If pressure drops unexpectedly, it could indicate a leak somewhere in the primary system. One of the most significant events in reactor operation. Coolant flow. The rate at which coolant is circulating through the core. If a coolant pump stops, flow drops, and the reactor must be shut down quickly enough that the fuel does not overheat. These four parameters: power, temperature, pressure, flow, are the vital signs of the reactor. They are monitored continuously by multiple independent instruments, with alarms set to alert the operators if any of them moves outside the expected range. Below these top-level parameters is a hierarchy of secondary and tertiary parameters. The status of every valve, every pump, every electrical circuit that supports the primary systems. Each of these has its own monitoring instrument, its own alarm set points, its own procedures for what the operators should do if something changes unexpectedly. The total number of parameters being monitored in a modern nuclear power plant control room is in the thousands. Most nights, nothing happens. This is the reality of nuclear power plant operations that rarely makes it into public discussion. Because nothing happening is not a story. The plant runs. The operators watch. The parameters stay within their expected ranges. The hours pass, but there is a discipline in this watching that is easy to underestimate. Attention, maintained over hours, in the absence of stimulus, is one of the most demanding cognitive tasks that human beings perform. The aviation industry has studied it extensively. The phenomenon of pilots becoming inattentive during long, uneventful flights, failing to notice gradual changes that would have been obvious during a period of active engagement. The nuclear industry has studied it as well, developing procedures and practices specifically designed to maintain operator alertness during quiet periods. Operators conduct regular tours of the plant, physical walks through the equipment areas, looking and listening and smelling as well as reading instruments. Because the control room displays tell you what the instruments are measuring, but a physical tour tells you things the instruments might not capture. The smell of hot insulation, the sound of a pump running slightly differently than usual, the vibration of a valve that is not quite seated correctly. Experienced operators develop a physical sense of the plant, a learned familiarity with how things sound and feel and smell when everything is right, that makes the subtle wrongness of a developing problem perceptible before it shows up clearly on an instrument. This kind of knowledge cannot be taught in a classroom. It accumulates through years of working in the same plant, and it is one of the reasons that nuclear utilities work hard to retain experienced operators, and why the institutional knowledge of a plant's workforce is treated as a genuine asset. At some point during the night, something will change. It might be minor. A feedwater control valve cycling more frequently than usual. A small pressure fluctuation in one of the steam generators. An instrument that needs recalibration. These small events are the texture of normal operations. They require attention, documentation, perhaps a notification to the maintenance department. But they do not threaten the safety of the plant. Or something more significant might happen. A reactor coolant pump might trip, lose power, and stop running. This reduces coolant flow through the core, and the reactor responds with a rapid, automatic power reduction. The operators respond according to procedures that have been practiced hundreds of times in the simulator. A full-scale replica of the control room in a separate building connected to a computer model of the plant rather than to the actual plant used for training and for testing procedures without any risk to the operating plant. The procedures exist for every credible event, not just the events that have occurred before, but the events that analysis has determined could occur. Each procedure is a careful, step-by-step guide to what the operator should do, and in what order, written by engineers, reviewed by other engineers, validated in the simulator, updated when operating experience or regulatory requirements demand it. When something happens, the operators do not improvise. They follow the procedures. This is not a limitation on their judgment. It is the systematic application of the collective judgment of hundreds of engineers and operators who analyzed every credible scenario and determined in advance what the correct response should be. The operator's judgment is applied to recognizing the situation correctly and applying the correct procedure. Skills that require genuine expertise. Not to inventing a response on the spot. The shift change happens at 6 in the morning or at 7. Depending on the plant's schedule, the incoming operators arrive before the outgoing shift ends. There is a formal handover. The outgoing reactor operator briefs the incoming reactor operator on the current state of the plant. Every parameter of significance, every piece of equipment in a non-normal status, every test in progress, every notification pending. The briefing is documented. Both operators sign the shift log to indicate that the handover has occurred and that the incoming operator has accepted responsibility. Then the outgoing operator leaves. The incoming operator sits down at the console. They conduct their own scan of the panel, checking that what they were told matches what the instruments are showing, confirming the status of every system they were briefed on. Then they settle in. Outside, the sun is rising. The plant does not notice. The reactor is still at full power. The turbine is still spinning. The generator is still producing electricity. The shift has changed. The watchers have changed. The watching continues. Here is the thing that is hardest to convey about life in a nuclear power plant control room. It is, on most days, unremarkable. The people who work there are not heroes in any visible sense. They are not doing something dramatic or dangerous or visibly important. They are sitting in a room, watching instruments, following procedures, documenting what they observe. But the system they are watching, the chain of processes from the fissioning uranium in the core to the electrons flowing through the grid, is producing electricity for hundreds of thousands of homes. It has been producing that electricity for months without interruption. It will continue producing it for months more. The unremarkableness is the achievement. The goal of a nuclear power plant is not to be exciting. The goal is to be reliable, predictable, safe, continuously available. The measure of success is not the dramatic moment handled well, though those moments exist and the training for them is taken seriously. The measure of success is the quiet night, the shift that passes without incident, the scan of the panel at 4 in the morning that shows everything normal, everything within range, everything as it should be. The operator who looks at the instruments, makes a note in the log, and settles back in the chair for another hour of watching. Outside, the city sleeps. The plant runs. The reactor burns its quiet nuclear fire in the dark. And the lights stay on. There is a question that almost everyone asks when the subject of nuclear power comes up. Not about how it works, not about where the fuel comes from, or how the electricity gets to their house, not about the control room, or the operators, or the procedures. The question is always the same. What happens when it goes wrong? It is a reasonable question. It is, in many ways, the most important question, because the history of nuclear power includes moments of failure that are among the most dramatic and consequential industrial accidents in human history. Events so significant that they changed the course of energy policy in multiple countries, reshaped public understanding of nuclear technology, and left physical landscapes that will remain altered for generations. To understand nuclear power honestly, not the version promoted by its advocates or condemned by its critics, but the actual, complicated, historically grounded reality. You have to understand these events, not the mythology around them, not the simplified narratives that reduce them to either proof that nuclear is uniquely dangerous or proof that nuclear is irrationally feared. The actual events, what happened, why it happened, what it meant, what changed afterward. Tonight, we are going to look at 3 of them, 3 accidents, 3 different reactors, 3 different causes, 3 different consequences, and one underlying lesson that runs through all 3, visible only when you look at them together. 3 Mile Island, March 28, 1979. The reactor was called Unit 2. It sat on 3 Mile Island, a narrow strip of land in the Susquehanna River near Harrisburg, Pennsylvania, surrounded by farmland and small towns whose residents had grown accustomed to the presence of the nuclear plant the way people grow accustomed to any large industrial facility, noticing it occasionally, thinking about it rarely, assuming without much examination that the people who built it and ran it knew what they were doing. Unit 2 had been operating commercially for less than a year when the accident began. The date was March 28, 1979. The time was 4:00 in the morning, the same quiet hour we visited in the previous chapter, when the plant is running and the operators are watching, and nothing in particular is expected to happen. At 4:00 a.m., the feedwater pumps stopped. The feedwater pumps are the machines that supply water to the steam generators, the component that transfers heat from the primary coolant loop to the secondary loop that produces steam for the turbines. When the feedwater pumps stop, the steam generators stop receiving their water supply. The heat transfer from the primary loop decreases. The primary coolant gets hotter. The reactor's automatic systems responded correctly. A turbine trip, an automatic shutdown of the turbines. Then a reactor trip, an automatic shutdown of the chain reaction, with the control rods fully inserted into the core. So far, everything was working as designed. And then a valve opened. The valve was called a pilot-operated relief valve, or PORV. It was positioned on top of the pressurizer, the component that maintains pressure in the primary coolant loop. Its purpose was to open if the pressure in the primary loop rose too high, releasing coolant to reduce the pressure, and then to close again once the pressure had returned to normal. The pressure rose, as expected, given the reactor and turbine trips. The PORV opened, as designed, but then it did not close. The valve stuck open. This was a mechanical failure. A simple, unglamorous, entirely mundane mechanical failure of the kind that occurs in industrial equipment with some regularity, and that, in any other context, would be a minor maintenance issue requiring attention but not representing a crisis. In this context, a stuck-open PORV was the beginning of something much more serious. With the valve stuck open, coolant was draining continuously from the primary loop. Pressure was falling. Temperature was rising. The operators in the control room needed to know this was happening. They had an instrument that should have told them. The instrument showed them the status of the solenoid that controls the PORV, the electrical signal commanding the valve to open or close. When the pressure normalized and the command signal changed from open to close, the instrument showed that the valve had received the close command. The instrument did not show whether the valve had actually closed. The valve had received the command. It had not obeyed it. The operators looked at an instrument that said "close command sent" and interpreted it as "valve closed." It was a reasonable interpretation, given the instrument available to them. It was wrong. With the PORV stuck open and the operators believing it was closed. The situation developed in a way that the people in the control room could not fully understand, because the picture they were building of what was happening was based on incorrect information. Coolant continued to drain, another instrument added to the confusion. The pressurizer water level indicator showed the water level rising, which, in normal operation, indicates that the primary loop is well supplied with coolant. The operators, trained to watch this indicator, saw the rising level and concluded that there was adequate coolant in the system. What was actually happening was more subtle. The loss of coolant through the stuck P-or of was causing the remaining coolant to boil partially. Steam was forming in the primary loop. Steam takes up more volume than liquid water, so the water level in the pressurizer rose. Not because there was more water, but because the mixture of water and steam was expanding. The operators were looking at an indicator that appeared to show a normal or even high coolant level, while the actual water inventory in the primary loop was declining toward a dangerous level. They took actions based on what the instruments were telling them. The instruments were telling them something that was not entirely representative of reality. For approximately 2 hours and 20 minutes after the accident began, the situation continued to develop without the operators fully understanding what was happening. The emergency core cooling system, the automatic system designed to inject large quantities of water into the reactor in exactly this kind of situation, had activated automatically and was doing its job. But the operators, seeing the pressurizer level indicator showing high, concluded that too much water was being injected and throttled the emergency cooling system back. This was exactly the wrong action, but it was the logical action given what the instruments appeared to be showing. At approximately 6:22 a.m., a shift supervisor who had just arrived at the plant looked at the full picture of what was happening and recognized something that the operators who had been managing the situation for 2 hours had not been able to see. The P-orb was probably stuck open. He identified the backup block valve, a separate valve that could be closed to isolate the stuck PORV, and ordered it closed. The coolant loss stopped. But by this point, the reactor core had been partially uncovered. The upper portions of the fuel rods had been without adequate cooling for a period of time. They had overheated. Some of the zircaloy cladding had failed. Some of the uranium fuel had melted. The core had partially melted. The containment building held. This is the fact that determined the outcome of the 3 Mile Island accident. The thick concrete dome surrounding the reactor, designed to contain the consequences of exactly this kind of event, performed its function. Radioactive material remained inside the containment. The radioactive gases and water that escaped the primary system entered the containment building rather than the environment. Some radioactive gas was released to the atmosphere during the following days, releases that were managed, and monitored, and that resulted in radiation doses to the surrounding population that were by the best available epidemiological evidence too small to produce detectable health effects. No one died from radiation exposure at 3 Mile Island. The reactor core was severely damaged. The cleanup took years and cost billions of dollars, but the containment held. The barriers between the radioactive material and the public performed as designed. The lessons of 3 Mile Island were not primarily technical. The reactor design had not fundamentally failed. The safety systems had activated as designed. The containment had worked. What had failed was the human interface between the reactor's actual state and the operator's understanding of that state. The investigation that followed, conducted by a presidential commission led by Dartmouth College President John Kameny, producing a report that became known as the Kameny Commission Report, concluded that the fundamental problems at 3 Mile Island were not equipment failures, but management failures, training failures, and failures in the design of the human factors, the instruments and procedures, and control room layouts that were supposed to help operators understand what was happening in their plant. The PORV indicator that showed command status rather than valve position was redesigned. Control room design standards across the industry were revised to make the most critical information clearer and more directly accessible. Operator training was fundamentally restructured. A new organization, the Institute of Nuclear Power Operations, was created by the nuclear industry to share operating experience and promote best practices across all American plants. The accident that caused no deaths led to changes that made nuclear power safer, not despite the accident. Because of it, Chernobyl, April 26, 1986. The reactor was called Unit 4. It was located at the Vladimir Ilyich Lenin Nuclear Power Plant, near the city of Pripyat in Soviet Ukraine, a city that had been built specifically to house the workers and families of the nuclear plant, a model Soviet city of 50,000 people that had existed for barely a decade. When the accident destroyed it, the reactor was a design called the RBMK, a Soviet acronym for High Power Channel Type Reactor. It was a large graphite-moderated reactor cooled by boiling water, capable of producing 1,000 megawatts of electrical power. It had a characteristic that its operators were aware of, but did not fully appreciate the danger of under certain conditions, particularly at low power, with a particular combination of coolant temperature and control rod position. The reactor became more reactive when its coolant boiled. Steam bubbles in the coolant, instead of reducing the chain reaction as they would in a pressurized water reactor, actually increased it. Physicists call this property a positive void coefficient. In a pressurized water reactor, the design used in the United States, France, Britain, and most of the world, a positive void coefficient is designed out of the physics of the reactor. If coolant boils or is lost, the chain reaction slows automatically. The reactor has an inherent tendency toward stability. The RBMK, under certain conditions, had an inherent tendency toward instability. This was known. It was documented. It was understood at some level by the designers and by the regulatory authorities. It was not, in April of 1986, fully understood by the operators of Unit 4 at Chernobyl. The accident began with a test. The test was designed to determine whether the turbines of Unit 4, coasting down after an emergency shutdown, could generate enough electricity to power the reactor's own coolant pumps during the brief interval, approximately 60 to 75 seconds between the shutdown and the startup of the emergency diesel generators. It was a reasonable test to run. The question it was designed to answer was a genuine safety question. If the coolant pumps lost power during an emergency shutdown, even for 60 seconds, the consequences could be serious. The test had been attempted 3 times before, in 1982, 1984, and 1985. All 3 previous attempts had been inconclusive for various reasons. The 4th attempt was planned for April 25, 1986. What happened over the following 24 hours involved a combination of schedule pressure, management decisions, operator errors, and the fundamental physical instability of the reactor at low power. Each factor interacting with the others, each one making the next step more likely, in a sequence that accident investigators would later call a cascade of errors. The reactor was being powered down in preparation for the test when the grid controller in Kiev asked that the power reduction be delayed. The plant was needed on the grid. The power reduction was halted, and Unit 4 ran at half power for approximately 9 hours before the test could resume. When the power reduction resumed late that night, an operator error caused the reactor's power to fall much lower than intended, to approximately 30 megawatts, far below the 700 to 1,000 megawatts at which the test was supposed to be conducted. The shift foreman made the decision to bring the power back up to the test level. At low power and in the physical state the reactor was now in, with a large number of control rods inserted and with the coolant at a particular temperature, the RBMK's positive void coefficient was at its most dangerous. The reactor was in an unstable condition that its designers had identified as a region to be avoided. The operators were not fully aware of this. The relevant safety regulations had not been clearly communicated. The plant's safety procedures did not explicitly prohibit operation in this state. The power was brought up to approximately 200 megawatts, still far below the intended test level, but the decision was made to proceed. At 1:23:04 a.m. on April 26, 1986, the test began. 20 seconds later, a reactor operator noticed that the power was rising uncontrollably. The shift foreman ordered an emergency shutdown. All the control rods were commanded to insert simultaneously, at 1:23:40 a.m., 36 seconds after the test began. The power excursion reached its peak. In approximately 3 seconds, the reactor's power rose to approximately 30 times its maximum rated output. The fuel shattered. Steam explosions ruptured the pressure tubes. The reactor core was destroyed. A second explosion, whose exact nature remains debated by physicists, with some believing it was a prompt criticality excursion, and others believing it was a steam explosion, blew the 1,000-ton reactor lid off the building. The graphite moderator, 1,700 tons of it, caught fire. The reactor was open to the atmosphere. What followed was the largest uncontrolled release of radioactive material from a nuclear facility in history. The graphite fire burned for 10 days. During those 10 days, radioactive material was released continuously into the atmosphere, carried by winds across Ukraine, Belarus, Russia, Scandinavia, and eventually across most of Europe. The immediate response required thousands of workers, many of them emergency responders, firefighters, military personnel, and plant workers, who were not fully informed of the radiation levels they were working in. 31 deaths were directly attributed to the accident in the immediate aftermath. 2 workers died in the explosions. 29 died of acute radiation syndrome in the weeks that followed. The city of Pripyat, 50,000 people, was evacuated 36 hours after the accident. Residents were told to bring enough for 3 days. Most of them never returned. The exclusion zone around Chernobyl covers approximately 2,600 square kilometers. 38 years after the accident, it remains largely uninhabited by permanent residents, though wildlife has returned in numbers that have surprised ecologists. The long-term health consequences of Chernobyl are genuinely difficult to quantify and remain a subject of scientific debate. The most directly attributable health consequence was an increase in thyroid cancer, particularly in children who consumed milk contaminated by radioactive iodine in the weeks after the accident. Approximately 6,000 thyroid cancer cases have been attributed to Chernobyl radiation exposure, the great majority of which were successfully treated. The broader cancer burden attributable to Chernobyl, above the normal background rate of cancer in the affected populations, has not been clearly detected in epidemiological studies. Though this absence of a detected signal does not mean the signal is not there. It may simply be too small to distinguish from the background rate. What Chernobyl demonstrated, in the starkest possible terms, was the consequence of a reactor design with an inherent physical instability, operated by people who did not fully understand that instability in a safety culture that prioritized production and schedule over the systematic identification and communication of safety risks. The containment building that had protected 3-mile islands surrounding population did not exist at Chernobyl. The RBMK reactor design had no full containment structure. This was a deliberate design choice. The RBMK was large enough that building a full containment dome over it would have been enormously expensive, and the Soviet regulatory framework did not require it. When the core was destroyed, there was nothing between the radioactive material and the atmosphere. This single design difference, the presence or absence of containment, was the largest factor determining the difference in consequences between 3 Mile Island and Chernobyl. No Western reactor design, no pressurized water reactor, no boiling water reactor, no reactor operating in the United States or Western Europe shares the RBMK's positive void coefficient. The physics of these designs are fundamentally different. The instability that made Chernobyl's accident possible does not exist in them, and all of them have containment buildings. Fukushima, March 11, 2011. The earthquake struck at 2:46 p.m. local time. It was magnitude 9.0, one of the 5 strongest earthquakes ever recorded, releasing energy equivalent to approximately 9,000 Hiroshima bombs. It struck approximately 70 kilometers off the Pacific coast of northeastern Japan, in a subduction zone where the Pacific tectonic plate pushes beneath the Eurasian plate. The Fukushima Daiichi nuclear power plant, operated by Tokyo Electric Power Company on the Pacific coast of Fukushima Prefecture, was approximately 180 kilometers from the epicenter. The earthquake shook the plant for approximately 6 minutes. The 6 reactors at Fukushima Daiichi responded exactly as designed. Units 1, 2, and 3, the units that were operating at the time, received automatic shutdown signals, and their control rods inserted fully within seconds of the earthquake beginning. The chain reaction stopped. The building sustained damage but remained structurally intact. The reactor pressure vessels were intact. The coolant systems were intact. The earthquake, by itself, did not cause a nuclear accident. What caused the nuclear accident arrived 41 minutes later. The tsunami warning systems had detected the earthquake immediately and issued alerts. The plant operators knew a tsunami was coming. The seawall protecting the Fukushima Daiichi plant was designed to withstand a tsunami of approximately 5.7 meters. The tsunami that arrived was approximately 14 meters tall. It overtopped the seawall by a margin so large that the seawall was effectively irrelevant. The wave traveled inland across the plant site, flooding the lower-lying areas, inundating buildings, destroying equipment. Most critically, it flooded the catchment areas, where the emergency diesel generators, the backup power systems that were providing electricity to the reactor cooling systems, after the grid power had been lost in the earthquake, were located. The generators stopped. Without electrical power, the pumps that circulated cooling water through the reactor cores could not operate. The reactors had been shut down. The chain reactions had stopped, but shutdown does not mean the fuel immediately becomes cold. A reactor core that has been operating at full power for months contains enormous quantities of radioactive fission products that continue to generate heat through radioactive decay. Even after the chain reaction stops, this decay heat is substantial. In the minutes after shutdown, It represents several percent of the reactor's full operating power. It decreases over time, but it decreases slowly. Hours after shutdown, significant decay heat remains. Without cooling, the decay heat caused the reactor cores to heat up. The water in the reactor vessels began to boil away. The fuel rods began to be uncovered. The events of the following days involved a combination of technical failures, communication failures, and the fundamental physical reality that 3 reactor cores were generating heat that their cooling systems could not remove. All 3 reactor cores melted to varying degrees. Hydrogen generated by the reaction between the extremely hot zircaloy fuel rod cladding and steam accumulated in the reactor buildings and exploded, causing significant structural damage. Radioactive material was released into the atmosphere and into the ocean. Approximately 154,000 people were evacuated from the area surrounding the plant. The evacuation was conducted under conditions of enormous stress and urgency, and the process itself had health consequences. Stress, displacement, disruption of medical care for elderly residents in particular. The direct health consequences from radiation exposure at Fukushima were, by the best available scientific evidence, small. One worker has been confirmed to have developed cancer that is attributed to radiation exposure during the accident. No deaths from acute radiation syndrome occurred. The Japanese government estimates that the evacuation and its associated stresses contributed to the deaths of approximately 2,200 people, primarily elderly residents of care facilities who were evacuated under difficult conditions. The cleanup of the Fukushima Daiichi site is ongoing. It will continue for decades. The cost is estimated in the hundreds of billions of dollars. The lesson of Fukushima was not about reactor design in the way that Chernobyl's lesson was about reactor design. The reactors at Fukushima Daiichi performed as designed when the earthquake struck. Their safety systems activated correctly. Their containments, though damaged by the hydrogen explosions, performed their basic function of limiting the release of radioactive material. The lesson of Fukushima was about assumptions. The assumption that a 5.7-meter seawall was adequate for the tsunami hazard at that site. The assumption that diesel generators located in basements would be available after a major earthquake and tsunami. The assumption that the most severe credible natural event had been correctly identified and prepared for. Each of these assumptions had been examined. Each had been found by the people examining them to be reasonable. Each turned out to be wrong. After Fukushima, nuclear plants around the world conducted thorough reviews of their natural hazard assumptions. Backup power systems were relocated to higher elevations or waterproofed. Additional layers of passive safety systems, systems that work without electrical power, using gravity and natural circulation, were required or accelerated. The assumption audit that Fukushima forced on the industry was uncomfortable and expensive. It was also necessary. The one lesson that runs through all three accidents. 3 reactors, 3 completely different causes, a stuck valve, and a misleading instrument, a reactor design with an inherent instability, and a safety culture that did not fully understand or communicate it. A tsunami that exceeded the design basis assumptions. But look at all three together, and something appears. In each case, the accident was the result not of a single catastrophic failure, but of a sequence of smaller failures: technical, procedural, organizational, cultural, that individually were manageable and together were not. In each case, people in positions of responsibility had information that could have changed the outcome, and that information was either not available, not understood, or not acted upon in time. In each case, the investigation that followed identified not just what had failed technically, but what had failed institutionally, what assumptions had not been questioned, what warnings had not been heard, what culture had allowed a chain of smaller failures to accumulate into something large. And in each case, 3 Mile Island, Chernobyl, Fukushima, the accident led to changes. Real, substantive, documented changes to reactor designs, to operating procedures, to regulatory requirements, to the safety culture of the industry. Nuclear power has learned from its worst moments in a way that other energy sources have not always learned from theirs. The coal industry has been killing people, miners, workers, and the public through air pollution for more than a century. The oil industry has spilled its product into oceans and burned its workers in explosions and poisoned communities. The natural gas industry has exploded pipelines and leveled neighborhoods. These events also led to changes. But the scrutiny applied to nuclear accidents, the depth of investigation, the breadth of consequent regulation, the seriousness with which each event is analyzed and learned from, is, by any comparison, unusual, because nuclear power is held to a standard that other energy sources are not. Whether that is appropriate, whether the fear that drives that standard is proportionate to the actual risk, is a question that reasonable people can debate and do. What is not debatable is the factual record: 3 significant nuclear accidents in 70 years of commercial operation, 31 direct deaths at Chernobyl, 1 confirmed radiation-related cancer death at Fukushima, no radiation-related deaths at 3 Mile Island. In the same 70 years, the burning of fossil fuels has caused air pollution that kills, by the best available estimates, approximately 7 million people per year globally. Every year, not in accidents. In normal operation, the comparison is not comfortable for anyone who has spent decades assuming that nuclear power is uniquely dangerous. But it is the honest comparison, and honesty, in the end, is the only way to understand something as important and as complicated as this. Everything we have covered tonight, every fact, every story, every accident, and every lesson has been about fission, citing things apart, taking a heavy atom, striking it with a neutron, and watching it divide into smaller pieces while releasing the energy that had been stored in the force, binding it together. This is what happens in every nuclear power plant currently operating on Earth. Every reactor in France, which generates approximately 70% of that country's electricity from nuclear power. Every reactor in the United States, which operates 93 reactors, producing approximately 20% of the nation's electricity. Every reactor in China, Japan, South Korea, the United Kingdom, Canada, and the dozens of other countries that have chosen nuclear power as part of their energy mix, all of them fission, all of them split uranium atoms. All of them operate on the principle that Enrico Fermi demonstrated in a squash court under a football stadium in Chicago on the afternoon of December 2nd, 1942. But fission is not the only way to release energy from the nucleus of an atom. It is not even the most powerful way. The sun does something different. Look up on a clear night and find a star. Any star will do. The bright one near the horizon, or the faint one near the center of the constellation, or the one you are not quite sure you are seeing until you look slightly to the side of it, and it becomes clear that star is not burning, not in the sense that a candle burns, or a coal fire burns, or the fossil fuels in a gas turbine burn. It is not combining chemical elements with oxygen to release the energy stored in chemical bonds. It is doing something fundamentally different, something that produces, weight for weight, approximately 1,000,000 times more energy than any chemical reaction. It is fusing atoms together. Inside the core of the sun, hydrogen nuclei, the simplest nuclei in existence, single protons, are being forced together under conditions of temperature and pressure so extreme that the quantum mechanical tunneling effect allows them to overcome their electromagnetic repulsion and merge. When two hydrogen nuclei fuse, they form a heavier nucleus, helium, and in the process, a small amount of mass is converted to energy. The same equation, E equals mc squared, the same conversion of mass to energy that powers fission. But in fusion, the energy released per unit of mass converted is even greater than in fission. And the fuel is not rare. It is not dangerous. It is not subject to the geopolitical tensions that surround uranium supply chains or the proliferations concerns that attend nuclear technology. The fuel for fusion is hydrogen, specifically two heavy isotopes of hydrogen, deuterium and tritium. Deuterium is present in ordinary water at a concentration of approximately 1 part in 6,000. Every liter of seawater contains approximately 33 milligrams of deuterium. The oceans of the Earth contain enough deuterium to power human civilization at current energy consumption levels for billions of years. Tritium is rarer. It does not exist in significant natural quantities, but it can be produced from lithium, which is abundant. The fuel for fusion is effectively unlimited. The waste product of the fusion reaction is helium, a light, inert, non-toxic gas, not radioactive waste that must be carefully stored for thousands of years, not carbon dioxide that accumulates in the atmosphere. Helium, which floats away harmlessly and is, if anything, mildly useful. Fusion produces no greenhouse gases. It produces no long-lived radioactive waste. It cannot melt down. A fusion reactor, if it loses containment, simply stops reacting. The plasma cools, the reaction ceases, and the worst outcome is that the reactor is damaged, not Chernobyl, not Fukushima, just a broken machine. If fusion is so much better than fission in every dimension that matters, more energy, more fuel, less waste, less risk, then why are we not already using it? Why? 70 years after the first hydrogen bomb demonstrated that fusion could release enormous amounts of energy, Are there no fusion power plants connected to any grid anywhere in the world? The answer is a problem of extraordinary physical difficulty. To fuse atomic nuclei, you must force them close enough together for the strong nuclear force to take hold. Close enough that the quantum tunneling effect can bridge the gap between them. And to get them that close, you must overcome the electromagnetic repulsion between their positive charges. The way to overcome that repulsion is heat, enormous heat, the kind of heat that does not exist anywhere on Earth outside of nuclear weapons, and, since December 2022, inside a very specific laboratory in California. The temperature required for hydrogen fusion is approximately 100 million degrees Celsius. 100 million. The surface of the Sun is approximately 5,500 degrees Celsius. The core of the Sun is approximately 15 million degrees, the temperature required for practical fusion on Earth must be higher than the core of the Sun because the enormous gravitational pressure of the Sun's mass provides a confinement that we cannot replicate on Earth, and higher temperature compensates for the lower pressure. At 100 million degrees, matter does not exist as a solid, liquid, or gas. It exists as plasma, a state in which electrons have been stripped from atomic nuclei, leaving a superheated cloud of charged particles moving at extraordinary speeds, dense with energy, and capable of destroying any physical material it touches. You cannot hold a plasma at 100 million degrees in a steel container. The steel would vaporize long before the plasma reached its target temperature. You cannot hold it in a ceramic container. Same problem. You cannot hold it in anything physical, because at those temperatures, there is nothing physical that will not immediately be destroyed. The solution that physicists developed in the 1950s, independently in the Soviet Union and in the United States, was to not use a physical container at all. Instead, use magnetic fields. Plasma is made of charged particles. Charged particles, moving through magnetic fields, experience a force that deflects their motion. If the magnetic fields are arranged correctly, in a specific geometry, with specific strengths, maintained with extraordinary precision, the plasma can be made to follow the field lines, rather than drifting outward to touch the walls of the vessel. The vessel does not need to touch the plasma. The magnetic field keeps the plasma away from the walls. This is the principle behind the tokamak, a donut-shaped device in which plasma circulates continuously around a toroidal chamber held in place by a complex arrangement of magnetic coils, heated by additional systems to the temperatures required for fusion to occur. The word tokamak is a Russian acronym for toroidal chamber with magnetic coils. It was developed by Soviet physicists Andrei Sakharov and Igor Tamm in the early 1950s. Sakharov, who would later become one of the Soviet Union's most famous dissidents and human rights advocates, began his career as a nuclear physicist working on fusion. For 7 decades, physicists and engineers around the world have been building increasingly large and sophisticated tokamaks, each one attempting to solve the central problem of fusion energy. The problem is this: to sustain a fusion reaction long enough to produce net energy, more energy out than was put in to heat and confine the plasma. You need to achieve a combination of plasma temperature, density, and confinement time that is technically described by a parameter called the triple product. For most of the history of fusion research, the triple product achieved by experimental reactors has been insufficient. The plasmas have been hot enough, or dense enough, or confined long enough, but not all three simultaneously, and not all three simultaneously at a level that produces more energy from fusion than was consumed in creating the conditions for it. The joke in physics circles, heard at conferences and in laboratory corridors for decades, was that practical fusion power was always 30 years away. In 1970, fusion was 30 years away. In 1990, fusion was 30 years away. In 2010, fusion was 30 years away. The joke had a long run, and then something happened. The National Ignition Facility is located at the Lawrence Livermore National Laboratory in Livermore, California, a research institution that has been involved in nuclear weapons design since the 1950s, occupying a campus of low buildings in the rolling hills east of San Francisco Bay. The NIF is not a tokamak. It uses a different approach to fusion, one called inertial confinement, in which a tiny pellet of fusion fuel is compressed and heated so rapidly that fusion occurs before the fuel has time to fly apart. The mechanism for this compression and heating is lasers. .192 lasers, the largest laser system ever built. The laser beams travel through a building the size of several football stadiums, are amplified and redirected and focused and converge simultaneously on a target chamber about the size of a large room. At the center of the target chamber sits a small gold cylinder called a Hohlraum, German for hollow space. Inside the Hohlraum is a spherical capsule approximately 2 millimeters in diameter, roughly the size of a BB pellet. The capsule is made of a plastic ablator material and filled with frozen deuterium tritium ice. The fusion fuel, when the 192 laser beams strike the Hohlraum, they heat it so rapidly that it emits X-rays. The X-rays strike the outer surface of the capsule simultaneously from all directions, ablating the surface material, vaporizing it instantaneously. The reaction force of the ablating material acts like a rocket engine, compressing the capsule inward from all sides simultaneously. The compression is extraordinary. The capsule shrinks from 2 millimeters to approximately 70 micrometers, smaller than the width of a human hair, in a few billionths of a second. The pressure at the center reaches approximately 300 billion times atmospheric pressure. The temperature reaches 100 million degrees. The conditions for fusion for decades. The NENIF had been approaching ignition, the point at which the fusion reaction produces enough energy to sustain itself. Without additional external heating, each shot produced more energy than the one before. The experimenters tracked the progress on graphs, watching the yield climb through years of increasingly precise experiments. On December 5, 2022, the 192 lasers delivered 2.05 megajoules of energy to the target. The fusion reaction produced 3.15 megajoules, more energy out than in ignition. for the first time in human history. A controlled fusion reaction had produced more energy than was delivered to the fuel to start it. The scientists who had been working toward this moment for years, some of them for their entire careers, received the news with the particular mixture of elation and exhaustion that follows the achievement of a long-sought goal. The laboratory director, Kim Boudil, announced the result at a press conference the following day. She said it was one of the most significant scientific achievements of the past half-century. She was not overstating it. But here is the honest accounting that followed the celebrations. The 3.15 megajoules produced by the fusion reaction was more than the 2.05 megajoules delivered to the target. That ratio, output to input at the target, exceeded 1 for the first time, but producing the 2.05 megajoules of laser energy required approximately 300 megajoules of electrical energy from the building's power supply. The overall energy ratio, the ratio that matters for a power plant, was still far less than 1. The NEF is a research facility, not a power plant. Its lasers are not designed for efficiency. They are designed for the particular pulse characteristics required for the experiment, not for the kind of continuous, efficient operation that a power plant would require. The path from the NEF's December 2022 result to a fusion power plant connected to the grid involves engineering challenges of a scale and complexity that will take decades to address. More efficient lasers, or different confinement approaches. Materials that can withstand the neutron bombardment from continuous fusion reactions over years of operation. Methods for breeding tritium from lithium inside the reactor. Heat exchange systems. Turbines. Generators. All the engineering that surrounds the fusion core, which must be designed, built, tested, refined, and made commercially viable. None of this will happen quickly, and yet the door has opened. The principle has been demonstrated. The fundamental physics, the hardest part, the part that took 70 years, has been shown to work. The energy is real. The reaction is possible. What remains is engineering. And human beings are very good at engineering. There is another path to fusion that has moved faster in recent years than anyone in the mainstream fusion community expected: private companies. The fusion landscape in 2026 includes dozens of private companies pursuing different approaches to fusion energy: tokamaks, stellarators, inertial confinement, magnetized target fusion, field-reversed configurations. Companies with names like Commonwealth Fusion Systems, TAE Technologies, Helion Energy, and many others, funded by venture capital and by the growing recognition among investors that energy technology is among the most important sectors of the coming decades. Commonwealth Fusion Systems, a spin-off from MIT, is building a tokamak called Spark, using high-temperature, superconducting magnets that are significantly stronger than the magnets in previous tokamaks. Stronger magnets mean smaller plasmas can achieve the required conditions. A smaller plasma means a smaller reactor. A smaller reactor means lower cost and faster development. Spark is designed to achieve net energy gain, the same threshold the NIF crossed in December 2022, using a machine that is far smaller and far simpler than ITER, the international mega project that has been under construction in southern France since 2010. And that is not scheduled to achieve first plasma until the mid-2030s. If the high-temperature superconducting magnet approach works as its proponents believe it will, the timeline for practical fusion power could compress dramatically, not to 30 years, perhaps to 10, perhaps fewer. Here is what the world might look like if fusion succeeds. Electricity generated from seawater, not from uranium mined in Kazakhstan, or coal mined in Appalachia, or natural gas extracted from shale in Pennsylvania. From seawater, which covers 70% of the Earth's surface and is, for all practical purposes, unlimited. No greenhouse gas emissions, no air pollution, no long-lived radioactive waste, no proliferation risk. The materials involved in fusion are not usable in weapons, power plants that can be built anywhere: cities, island nations, landlocked countries with no fossil fuel resources of their own. Because the fuel is water, electricity cheap enough that energy poverty. The condition of approximately 700 million people alive today who lack reliable access to electricity becomes a solvable engineering problem rather than an intractable economic one. This is not a utopian fantasy. It is a physical possibility. The fuel exists. The physics works. The engineering is difficult but not impossible. Whether it arrives in 10 years or 30 or 50 depends on choices being made right now in government laboratories and private companies and university physics departments and the funding agencies and investors and policymakers who decide how much of humanity's resources to direct toward this particular problem. It will not come without investment. It will not come without patience. It will not come without the willingness to fund science, whose payoff is decades away, in a world that increasingly rewards quarterly returns. But it can come, and if it does, the story that began with Lise Meitner walking in the snow in Sweden in December 1938, working out what it meant that a uranium nucleus had split, will have reached an end that Meitner could not have imagined. The same fundamental force, the same E equals mc squared, the same conversion of a tiny amount of mass into an enormous amount of energy. But this time, the fuel is the ocean, and the waste product is helium, the switch on the wall. One more time you flip a switch, a light comes on. You know now, in a way you did not know at the beginning of tonight, what actually happened somewhere inside a building surrounded by thick concrete walls. Uranium atoms are splitting. Neutrons are moving through moderator and coolant. Fission products are generating heat. Coolant is carrying that heat to steam generators. Steam is rising through pipes to turbines. Turbines are spinning generators. Generators are producing current. Transformers are stepping up the voltage. Transmission lines are carrying the power across miles of countryside. Substations are stepping the voltage down. The wire behind your wall is carrying the electrons. Your finger on the switch. The chain reaction in the core, connected. And somewhere, in a laboratory in California, in a research institute in France, in a startup company in Cambridge or Tokyo or Seoul, someone is working on a different fire. Not uranium this time, hydrogen. deuterium, tritium, the lightest elements in the universe, forged in the first minutes after the Big Bang, present in every liter of seawater on Earth, the fire that powers the sun, being coaxed slowly and with extraordinary patience into a form that human beings can use. Tonight began with a simple question. You flip a switch, a light comes on. What actually happened? We followed the answer backward through and the transformer and the generator and the turbine and the steam and the coolant and the fuel rod and the uranium pellet and the chain reaction, all the way to the nucleus of an atom, to the marble in the stadium, and to the force that binds it together and the energy that is released when that force is overcome. We met Lise Meitner in the snow, working out an equation that would change the world. We met Enrico Fermi in the squash court, calm enough to stop for lunch before changing it. We met the operators who watched the reactor through the quiet hours of the night. We met the engineers who learned from 3 Mile Island and Chernobyl and Fukushima what must never be allowed to happen again. And we stood, briefly, at the edge of what might come next, the energy of stars, available to everyone from the ocean. The reactor is still running. Right now, while these words settle into the quiet of the room around you, the chain reaction is sustaining itself in its careful, controlled, precisely managed way. The coolant is circulating, the steam is rising, the turbines are spinning, the light in your ceiling is on because of a process that began in the heart of a dying star, a star that exploded billions of years ago, scattering heavy elements through a region of space that would eventually become our solar system, depositing uranium in the crust of a planet that would eventually develop life sophisticated enough to understand what uranium contains. The light is old in that sense, older than the Earth, older than the sun, stored in atomic nuclei for billions of years, waiting for a species curious enough to find it and careful enough to use it. You flipped the switch, the light came on, Nesmieft well.